Hey guys, it's Mr. Woodward again. Let's talk about the blowgun demo, the long and short blowguns. And let's first begin by titling our notes, Impulse Momentum. And the opening question is, why did the longer blowgun cause the marker cap to move faster? What was the difference between what the marker cap experienced in the long blowgun compared to the short blowgun? And the first question is, did the marker cap receive more force from one of the two blowguns? No, it didn't receive more force from one or the other because the force it received was the force from my mouth both times, and I blew with the same pressure both times, so I gave it the same amount of force. What was the difference? The difference is that it received the same amount of force for more time, and time is the difference. Up until now, we haven't been thinking about forces applied over a period of time, but now we're going to start thinking about what's the effect of applying a force for more time. When the longer blowgun delivered more force for more time, it delivered more impulse. This is a key word, impulse to the marker cap. And so impulse is related to force and time. Here's our definition of impulse. Impulse is a force applied for a period of time. So it's going to be the product of force times time gives us something called impulse. By the way, if at any point I'm moving too fast through this video, feel free to pause it, get caught up, and then hit play and we'll keep going. So let's look at an example of this thing called impulse, which is force measured over a period of time. And in the first example, let's look at the pen cap in the different blowguns. So in example 1, calculate the impulse applied to the pen cap while it was in the long blowgun, and we're assuming that was in the long blowgun for 0.03 seconds, so not that much time, compared to the short blowgun in which the pen cap was in that short blowgun for 0.02 seconds, so less time, 0.03 in the long blowgun compared to 0.02 in the short blowgun. And then I have to tell you that the pen cap has a 4-gram mass, and both pen caps receive 9 newtons of force. So what's the impulse? Well, here's our definition of impulse. Impulse is force multiplied by time, and you're going to want to write this one down. This is a key equation for this unit. Impulse is force times time. So when we measure the impulse of the long and short blowguns, we're going to multiply their forces by their times. And it actually will have nothing to do with this mass. We can skip the mass. So the impulse of the long blowgun compared to the impulse of the short blowgun, as we calculate this stuff, is the long blowgun has 9 newtons for 0.03 seconds, gives us 0.27 newton seconds of impulse, which, by the way, actually simplifies to 0.27 kilogram meters per second. And the short blowgun has an impulse of 9 newtons times 0.02 seconds, which gives us 0.18 newton seconds, which is the same as 0.18 kilogram meters per second. So we can clearly see that the long blowgun gives the marker more impulse than the short blowgun does. And unfortunately, this weird unit, kilogram meter per second, there is no way to simplify this. We don't have a fancy new name for that unit, so we can just call it units of impulse, kilogram meters per second. All right, let's move on to a second idea. First of all, recall from Newton's laws, and you can skip this part, that mass is a measure of inertia. This is Newton's first law. Mass is a measure of inertia. And the question is, which pen cap had more inertia? Well, both pen caps were identical. They both had the same mass. So since they have equal masses, they have equal inertias. If they have equal inertias, why did one pen cap create a greater impact on that box than the other one did? They have equal inertias. Shouldn't they be equally difficult to stop? Well, they both had inertia in motion. And inertia in motion is actually called something new. It's called momentum. Which pen cap had more momentum, inertia in motion? Well, let's take a side note before we answer that question. What is momentum exactly? Here's our side note. Momentum is inertia in motion. So it's very, very similar to inertia. It's just that there can be no momentum of rest. In other words, if there's no motion, there's no momentum. And we have an equation for momentum, just like we had an equation for impulse. Momentum, which we use the letter P. Why? Because M is already taken for mass, so they had to use a different letter. Momentum P is equal to mass times velocity. Here's our momentum equation. Momentum is mass times velocity. So if something is not moving, it has no velocity and therefore no momentum. So back to our question, which pen cap had more momentum? Well, since the pen cap from the long blowgun moved faster, it had more velocity, it had more momentum. Equal masses, but the long blowgun produced more velocity. Therefore, that pen cap had more momentum. Let's take a look at an example of momentum. Think about an apple falling from a tree, so it's got both mass and velocity. An apple falls from a tree and reaches a speed of 5 meters per second before hitting the ground. If the apple has a mass of 0.1 kilograms, how much momentum does it gain? Well, we start with our momentum equation. Momentum is mass times velocity. And we just plug in the numbers. The apple has 0.1 kilograms of mass and 5 meters per second of velocity. So multiplying those together gives us 0.5 kilogram meters per second. Those are funny looking units, but there's no name for units of momentum. So we just leave it like that. Now what's really nice about these units is they are the same as the units of impulse. So momentum and impulse are both measured in the same units. Could they possibly be related? They're both measured in the same units. Are momentum and impulse possibly related? They are. Momentum and impulse are definitely related. And they are related this way. How are impulse and momentum related? Well, impulse causes a change in momentum. So if you apply a force over a period of time, it will cause an object to move and gain momentum. Or if you apply a force over a period of time, it will cause an object to stop and lose momentum. And so what we can do is actually equate impulse to a change in momentum. Force times time equals delta, there's our Greek letter representing change, delta mv, a change in momentum. And this is called the impulse-momentum relationship. So this is a hugely, hugely important equation. So now we're relating impulse and momentum to each other. And we can say that an impulse is equal to a change in momentum because it causes a change in momentum.